person who doesn't know anything about it as an ABC explanation, what is quantum teleportation?
Yeah. So, you know for sure the Star Trek model of teleportation, which is basically that somehow someone dissolves somewhere, right?
Interesting.
And then is put together at another point, a remote place, right? But the point is that this is not exactly what we are doing in quantum teleportation, right? So in quantum teleportation, we have some system and we can transfer the state of that system. So maybe its velocity and its position to some other system that is then relative to its frame in the same state. Possible to kind of eavesdrop on messages that are encrypted in quantum systems like photons, right? So it's a way to fight cybercrime.
Are there any ethical considerations around this? Because it sounds like, it sounds very interesting.
What I understood is they said that, this can be a threat, this new technology, because it might make the gap between rich and poor nations even bigger, even deeper.
What are some of the biggest challenges in trying to make quantum teleportation scalable or much more applicable?
And one of the things in this is that you have to build something which is known as a quantum memory. It is difficult to build these quantum memories, but so I would say that's one of the main challenges in quantum communication.
Hey guys, you already know that this is SA Science Spotlight, and as exciting as we've announced earlier on, we are the official media partner of the SAIP 2025 conference, and as promised, we're going to deliver you experts in the field and people who are keynote speakers at the conference. So all the exclusive content, you are definitely getting it from us. And talking about keynote speakers at the conference and experts in their field, right now we have a very important guest who goes by the name of Prof Thomas Konrad. I hope I said it right. So
you can leave away the prof. You can just call me Thomas.
All right, Thomas. Doesn't feel right, bro. But anyways, so Professor Thomas is a very well-respected quantum physicist, and he has done a lot of work in the space of quantum information theory and quantum teleportation. I know it sounds like big, heavy words, but we're going to go straight into it. He's based in KZN, and he has contributed so much in terms of theoretical and experimental frameworks in the space of quantum teleportation. So today we are joined by the non-infamous Professor Thomas Konrad. Thank you so much for joining us, Professor. Thank you. How's the conference so far? I know it's the first day. We still have 5 more days to go. How are you finding it?
I think it had a good start, you know. It's a little bit cold here in Johannesburg, I have to admit this.
Yes, especially in the mornings.
Yeah. But I mean, we are on 1,800 meters, I think.
Makes sense.
And that makes perfect sense.
Yes.
Everything is expected, and I think there is a good atmosphere. You know, there are students that ask questions. That's always the most important thing, that they get into it. You know, there is a threshold. You should ask a question, and then you feel much freer to ask the second question. So that's the point.
Thank you so much.
And it looks good.
Thank you. So, quantum teleportation, for a person who doesn't know anything about it as an ABC explanation, what is quantum teleportation? Because I'm hearing it from the first time today.
This is the thing. So, you know for sure the Star Trek model of teleportation, which is basically that somehow someone dissolves somewhere, right?
Interesting.
And then is put together at another point, a remote place, right?
Is it like one of those Marvel movies? Because I know
you know the Marvel movies.
Yes.
Okay. Yeah, I was referring to the Star Trek series.
Oh, the Star Trek. Okay.
Star Trek.
Yes.
You know Star Trek?
Yeah, I do.
Yeah, Captain Kirk and so forth.
Yes.
Scotty. There you have it, right? But the point is that this is not exactly what we are doing in quantum teleportation, right? So in quantum teleportation, we have some system, and we can transfer the state of that system. So maybe its velocity and its position to some other system that is then relative to its frame in the same state. Okay, or you could imagine you have a image, all right? Could even be a 3D image, so a hologram. Okay, I
Yeah.
can take basically all the light that is irradiating from you because it reflects from the lights
Right.
from the lamp. I could take that and make it appear in the room next door. That's basically it. Without that, the information is carried from here to the next door. There is some other information that I have to give them in the next room, but
Yeah.
it will not be about you.
Oh, okay.
So this is the kind of magic thing.
Does it actually work in practice, or is it still theoretical? And if it does, what are some of the key components that are involved in quantum teleportation?
Yeah, so it works in practice. I mean, in fact, one of the records has been set in this lab here. I think maybe on the ground floor, right?
Okay.
So 5 stories below us, no, 8 stories below us. There is the structured light lab,
Okay.
and they put together a device that could teleport an image that had 15 dimensions in some sense to a remote place, which was not really so remote, was just 3 meters apart, but it was a proof of principle thing. Yeah.
That's interesting. And is it taught in the labs? I know you're based in KZN.
Yes.
Is it something that is practically taught, or how do you relay that information? How do you deliver that content?
Yeah. So it's a quite spooky concept, you know, and people are always very surprised to hear about it, and it is less spooky at the moment because you know what they did. They had a really bright beam, okay, and they send it through a crystal together with a single photon. And then the single photon, this is one of the components that you need. You need a pair of photons that are entangled. Entangled means they are very highly correlated in a sense that supersedes all classical correlations. And then suddenly the image that was carried by this beam is now transferred to the single photon. A photon is an elementary excitation of a wave. Okay, so you can imagine you have a wave, okay, and if you go down with the amplitude until basically nothing is left, then the smallest amplitude that you can get is elementary excitation. That's a photon, right? So it's a very kind of sensitive and very small amount of energy that this photon carries, and that's why you cannot see it with your blanket eye. So you have to take pictures with devices and so forth, cameras and so forth, and then only you find that it is working.
Yeah.
And the point is now that actually what we discussed already today is it would be great if we could really teleport an image that is a bright image. So imagine you are appearing on the other side. I mean, it's just your image, not you yourself, right? But that can possibly be done. It's a little bit more work, and it's in the development stage, but it's good. And you can ask me what we need that for, of course.
Okay, what do we need that for?
I'm not the interviewer.
Because we want to know. You know,
So this is important if you want to have a long distance quantum communication. So quantum communication is a way of communicating so that no one can listen in. So there is something very strange about the quantum world. You know, it's the world of the microscopic particles. If I had a microscope, that was really fine, and I would see how all the molecules move around. That would be the world of quantum mechanics, and it's totally different than what we know from the world. And one of the differences is that you cannot copy information. So the state of a system, of a molecule, if you just give me the molecule, I can never find it out. Right? So therefore, I'm not without assistance. And therefore, it's impossible to kind of eavesdrop on messages that are encrypted in quantum systems like photons. Right? So it's a way to fight cybercrime in some sense. And you know, cybercrime is a big issue. So it's very important that we have something like this. And it gets even more important. Let me tell you this. So, you know, the usual way we try to make communication secure is we encrypt data using
Yes,
mathematical
yes.
algorithms,
Agreed.
right? And these algorithms, for example, if you go to your ATM, you punch in your PIN,
Yeah.
then PIN is not just sent down the line, but it's actually one takes a very big number, a large number, and this number is used as a key that locks basically the message. So your PIN is somehow transformed into some other numbers, and if you don't know the factors, the prime factors of this big number, so for example 15 is not a big number, but has the factors 3 and 5, 3 times 5 is 15, right? And if you have a large number, it's very difficult to find these prime factors. It's
Yeah.
believed to be basically with classical computers impossible to find that in a reasonable time. And now there is a new technology called quantum computers, and they can find it very fast.
So in terms of like being secure, the system that is working right now, it's easily hackable. So what you're saying with quantum computing and
Yeah.
teleportation,
Yeah.
it's the safest and most secured system you'll ever find.
That's it.
Yeah.
So, and I wanted to point out that the usual encryption techniques, they are under threat from another technology, which is also quantum technology, namely quantum computers. So once we will have the quantum computer, and people estimate, depending on whether they are very careful or pessimistic or optimistic, between, let's say, 5 to 50 years. So it could be quite far away, right? Maybe it never happens.
Yeah.
But if it happens, then we can decrypt all the messages, and then this is even for military and for national and national interests. This is of big importance. So the people that don't have the technology to make it secure again, which is also done somehow by a quantum technology.
Yeah.
So quantum technology forms the threat and gives the solution.
Right.
It sounds like someone thought of this to sell a lot of devices,
Yeah.
but but it seems to be true as far as I can judge this.
I see.
So this is a big thing, and it's not only important in 10 years' time when the computer comes,
Yeah.
but already now, because I could now listen into the data transfer, store the data that is encrypted. I can't read it now, but in 10
Yeah.
years' time, when the quantum computer is there, I
Yeah.
decrypt it. And then I know what you said 10 years ago, and if this is sensitive in 10 years' time, then you better don't say it now. You understand?
I understand. Interesting. And it's so mind-blowing now that you
Yeah.
explained that. But I would love to know that, are there any ethical considerations around this? Because
Yeah.
it sounds
Oh.
like, it
Oh,
sounds
now we are
very, very
talking, huh?
interesting.
Yeah.
Yeah.
I can tell you one thing. So I went to the opening of the International Year of Quantum Science, which is this year, 2025, right? In Paris, at the UNESCO headquarters.
Right.
And they had 2 days. The first day was about science, and the second day was about the social impact of science. In the first day, I kind of thought I know this already, or
Yeah.
maybe this is arrogant, but I knew what they were talking. And the second day was a total surprise. And they said, and this is my interpretation, okay, so I have to be careful, but
Okay.
what I understood is they said that, this can be a threat, this new technology, because it might make the gap between rich and poor nations even bigger, even deeper.
Interesting.
You know why? Because the rich nations, they can develop this, and the poor nations, they have to follow, and they will just be clients, and that is kind of the one of the ethical things I see there.
Yeah.
And there are organizations like the UNESCO, but also others that try to kind of dampen these economic effects that would deepen the gap. I mean, no one wants the gap to be deepened except the rich, maybe.
Yeah.
But I mean, that's not ethical in my opinion.
Yes.
Do you agree?
I absolutely agree,
Okay.
Prof. Yeah. But it's such an interesting field now that you say that, and I'm quite interested right now. And it's not something that any person would know randomly lying around. So it's a very specialized field. How does a person get into such a field, and what does it take for you to get to be now a physicist?
Oh, you want to know that, huh?
Yes.
Okay, do you want to become one, maybe?
I think a lot of people who are watching
Okay.
might be influenced,
you
or
what
they're
it
trying to
takes.
find a career in physics. So
Yeah.
maybe
It takes only time. It takes 10,000 hours. So people say if you do something for 10,000 hours, and 10,000 hours is approximately 5 years if you work 40 hours a week, then you are an expert.
Okay.
And it doesn't, I think it doesn't matter what it is.
Okay.
Whether you are, okay, maybe you don't become a super football player or a super guitarist. I tried it, I didn't. But at least the normal things that we are doing, and physics is also a normal thing in my opinion.
Yeah.
That is, and it is, we are lucky, we can learn all that, you know. It's not like you have to be someone special. You have to just be very interested and have perseverance, you know. 10,000 hours and you are in the club.
That's interesting. So, Prof, before we let you go, I wanted to know that what are some of the biggest challenges in trying to make quantum teleportation scalable or much more applicable? So what are some of the challenges in terms of scaling or making it more practical in terms of...
So there is something that is related to it. So I said you actually need it as an ingredient in the secure communication networks that are far-reaching networks, and you need kind of you know, in order to not rely on trusted node where someone gets a message and then sends it on to the next node, you know, and must be trusted. But in order to automate it, you need to kind of connect. So there is something like systems that carry these correlations, and if you have a pair of such systems, you can connect them so that you get one system that is even further reaching, you know. So, and one of the things in this is that you have to build something which is known as a quantum memory, because sometimes one of these photons gets lost, right? And you have to basically store the information until you are sure that from both sides there is a connection. Then you can kind of fuse them and then make the form these correlations on a distance, right? And this is difficult to build, these quantum memories. But so I would say that's one of the main challenges in quantum communication.
Oh my gosh, I am so intrigued, and thank you so much for explaining and coming through to us. And I'm sure a lot of people, young people who are also in the space of physics, who are still starting out, but they don't know what to specialize in, and this could definitely be a great information session for them to join in. So thank you so much for joining us. Okay.